Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. I'm really excited about today's discussion. We've got some fascinating ground to cover, especially with the recent developments in, well, everything it seems.
Yeah, absolutely. It feels like things are accelerating so quickly, it's hard to keep up. I was just reading about that new AI model that achieved human level performance on a complex reasoning task. It's truly mind blowing.
Hold on, human level? I think that's a bit of a stretch, isn't it? It excelled at a very specific, predefined task. It's not like it can generalize to other kinds of problems or even understand why it got the answer right.
Exactly. It's like comparing a highly trained calculator to a child learning to count. The calculator is faster and more precise at calculations, but it does not grasp the underlying meaning of numbers. It can't use them to bake cookies. It's a classic case of mistaking narrow AI for general intelligence. I mean, it's impressive, don't get me wrong, but I think we're still pretty far from true AGI.
But isn't that progress still incredibly valuable? Even if it's not AGI, these models are pushing the boundaries of what's possible. And I'm particularly interested in how they might help us understand the brain itself. I mean, we're building machines that can mimic certain cognitive functions. Doesn't that offer insights into how those same functions operate in our own minds? We should be combining these advancements with neuroscience research.
Oh, absolutely. I think the mimic aspect is key there. Yes, these algorithms aren't identical to biological processes, but the way they learn and adapt can still inform our understanding of, for example, how neural plasticity works in the brain. The successes we've had in deep learning are, to me, a sign that we're on the right track. We're finally scaling up these networks to the point where they can extract complex patterns from data, very much like what the brain does. I mean, look at these massive language models. They can generate human-like text. That didn't seem possible just a few years ago.
And yet, they still fall flat on their face when faced with basic common sense reasoning or any real world ambiguity. They can generate text, but do they understand it? That's where I think we're fundamentally mistaken in believing that more data and bigger networks will solve everything. It's brute force, and it's inherently limited. We need to be looking at how the brain uses symbolic representations, how it integrates logic and inference, not just raw pattern recognition. This is where we need to think about neuro-symbolic approaches.
I'm with you on the brute force aspect. I think we are missing something fundamental, and you touched on an interesting point with representation. I'd argue that the key might lie not just in symbolic processing, but in how information is represented and transformed across different coordinate systems in the brain. I think current neural networks, even deep ones, are constrained by the single coordinate system of their architecture. They lack the kind of spatiotemporal flexibility needed for true general intelligence. We're building things that are amazing at pattern recognition, but that fundamentally don't have a unified understanding of the world. Think about how our brain uses allocentric and egocentric representations and seamlessly switches between them. A true AGI needs something that handles these transformations gracefully.
That's a really interesting way to look at it. I mean, you're basically saying that current models are too static, lacking the dynamic representational capacity that's inherent to biological intelligence, right? And yes, I completely agree on the need to think about multiple coordinate systems. Our brains aren't operating on a single static representation, and we need to take these findings from neuroscience and apply them to our AI research. And I think it really highlights the need for neuroscientists and AI researchers to collaborate more closely. But what about the advancements of deep learning? I mean, there are some incredible things being done. Surely we can't just dismiss that. Isn't it still useful for the building blocks of intelligence?
Absolutely. Dismissing deep learning entirely would be like throwing the baby out with the bathwater. Yes, it has its limitations and may not be the full story, but we have seen very impressive results in very specific scenarios that were not even thought possible just a decade ago. The way deep learning models learn hierarchical features, for example, is arguably similar to how the visual cortex works. I mean, it is not a coincidence that the models are loosely based on the biological structure. The algorithms used for image recognition today can identify objects with a level of detail that was unthinkable before. This shows a sophisticated ability to extract patterns and build an understanding that, at least to a degree, emulates the functions of our brains. It's about recognizing that deep learning isn't the final answer, but a key building block. Think of it as a powerful tool that can help us bridge the gap between data and higher-level cognition. And the more we learn about how these models fail, the more we'll learn about how true intelligence works.
But I think that's exactly the point. We're focusing on the how instead of the why. The image recognition software is a perfect example. It's an extremely powerful tool. It can identify a cat in a picture with incredible accuracy. But it doesn't know what a cat is. It has no concept of a cat's behavior, their place in the world, that they are fluffy, or that they meow. It's just a statistical association of pixels, and that's why it's so easily fooled by adversarial examples. And I'm not dismissing the advances we have made, but relying on pattern recognition alone is very short-sighted when we know the brain has logical inference and reasoning systems. We need to look at integrating reasoning systems. That's what will allow us to get true understanding. This is not something that purely deep learning can do. We need to move into hybrid systems.
Yeah, and I think this ties into my earlier point about coordinate systems. If all the information is represented in a single, static coordinate frame, how can the system generalize its understanding to new contexts and integrate new experiences with its existing knowledge? It's like being able to read a map, but only if it's oriented north up. As soon as the map is rotated or you need to switch to a globe, you are lost. For real intelligence, you need the ability to transform the information and understand it, irrespectively of the coordinate frame you use. It's not just about pattern recognition or symbolic representation, but about how these representations can be manipulated and related to each other across different frames. I mean, we as humans can switch between seeing the world from our own point of view and imagining the scene from another person's perspective effortlessly. Current AI systems just can't handle that level of dynamic representational flexibility.
This is fascinating. So, it's about creating a system that can handle these different representational frameworks. And that has the flexibility to move between these to create a complete understanding of a task or an environment. And this links to the symbolic approach that you were discussing earlier. It's about bridging the gap between the raw data we get from pattern recognition and the conceptual understanding that involves abstract symbolic reasoning. And to me, if we take the findings of how the brain handles these different coordinate systems and combine that with the strengths of the advances we have seen in AI, we might actually be on a path to building something that is truly intelligent, as well as giving us insights into ourselves.
I think you are spot on. And to me, the exciting part is that we are already seeing some of this emerge. I mean, we see things like attention mechanisms in deep learning, which are quite impressive. These allow the network to focus on the most relevant parts of the input and are directly inspired by the attentional mechanisms we observe in the brain. They can adapt the process of information and build a representation that is actually quite remarkable. We are learning more and more about how to build these kind of dynamic structures that are able to adapt to the context. And I do think that we will get a better, richer, more complex understanding of the world with these advances. Yes, they might be limited by the specific coordinate system they are built on. But the building blocks we are building are definitely taking us in the right direction. We shouldn't underestimate the power of scale. The more powerful these systems get, the more emergent behavior we see.
But emergent behavior can just as easily be seen as unpredictable and uncontrolled. And this is the danger of just throwing more data at an already flawed system. Attention mechanisms are useful, but they are still just a function on an array of data. They don't actually understand the meaning behind the patterns. We still need to figure out how to combine the power of the neural networks with symbolic reasoning. This is where we need to look at neuro-symbolic approaches and building systems that can bridge the gap between perception and cognition, something that can learn and understand the meaning of its experience, and not just the raw sensory input. We need algorithms that can reason, plan, and learn with the flexibility of a human mind. It's not just about recognizing a cat. It's about understanding what a cat is and being able to infer, for example, that it will not be a good pet for someone with severe cat allergies.
And this brings me back to the idea of how information is represented. Let's say we have that cat image. The pattern recognition algorithm can identify the cat, but the symbolic system has a symbolic representation of a cat. But how does the system translate between these two representations? How do they integrate so that a concept of a cat can be built? And how can that same concept be used in different contexts, with different sensory input? I think that this is where we are lacking the key fundamental algorithm. We don't have something that can handle the dynamic transformation across multiple coordinate systems and representations. And I suspect that if we can solve this problem, we'll unlock a whole new level of intelligence. And I think this is where we need to get inspiration from the brain, because it solves this problem so effortlessly. Maybe we need to look at how the different layers of the brain process the information across time and space, something akin to a spatiotemporal graph.
It's like we're talking about a fundamental issue of translation, isn't it? Between raw sensory data, symbolic representations, and even different internal coordinate systems. The brain somehow manages to convert all of these into a coherent understanding of the world. And to me, that is so inspiring. It highlights the potential for true synergy between neuroscience and AI, where we can take inspiration from the workings of the brain and combine it with the power of AI algorithms to create a system that is truly intelligent. Not only will it be a marvel of engineering, it will provide crucial insights into the workings of our minds. But as it stands, it feels like each of these different approaches, the deep learning and the symbolic approach, are like different parts of a puzzle that we haven't quite been able to put together yet. But we can see the advancements, And that to me is what gives us the optimism for the future.
Yes, absolutely. And I think we are building some very powerful tools. Deep learning has proven that it is incredibly useful, and the advancements have been truly monumental. Yes, it is not the entire picture, but the capabilities we have unlocked just with the advancements in deep learning are quite revolutionary. I think we are starting to see those pieces of the puzzle come together. I mean, we see architectures that incorporate aspects of symbolic logic and reasoning systems into deep networks. It's not a simple case of replacing one system with another, but more about finding the right balance. It's about creating systems that can combine the strengths of both approaches. We have the pattern recognition. We are starting to build more powerful attention mechanisms. It feels like we are starting to move in the right direction.
But the issue, to me, is the reliance on the emergence of intelligence from the scale. We're still not truly understanding how reasoning is built and integrated within these systems. If we just scale up current models without a fundamental understanding of how they can learn the structure and semantics of the world, we are just going to get very good pattern recognition that lacks the generalizability needed for true AGI. We still need to look at how the brain uses symbolic representations to build models of the world. This is where hybrid neuro-symbolic approaches can bridge the gap between pattern recognition and higher level cognition. We need to start looking at causal inference to tie off reasoning and logic. We need to start looking at causal inference, something deep learning is fundamentally not very good at. Without causal reasoning, these models will be limited in how they understand the world and plan for the future. We shouldn't be just focused on what can be done with large data sets, but what should be done to create a truly intelligent system.
And I agree with that. It is not just about pattern recognition, and I think it goes hand in hand with how information is represented. If the fundamental data structure is not appropriate for the task, then no matter how much data you throw at it or how complex your neural network becomes, it will not be able to solve that task. You can't build a house on sand, no matter how much sand you have. We need to have something that allows the system to transform representations gracefully between these different coordinate systems. I'm very interested in how the brain integrates spatial and temporal data. For instance, how does a visual scene become a memory? And how can we recall that memory with the relevant spatial and temporal information? I think that these insights are key in building an AGI, and current deep learning systems are fundamentally lacking this ability.
So, if we are thinking about future research directions, it feels like we need to focus on a more integrative approach. As someone who advocates the combination of AI and neuroscience, I would really love to see more research into the neurobiological foundations of these transformations, the ways the brain converts between different representations and coordinate systems. If we can understand these processes, we can build better algorithms and architecture for AI. I would love to see more focus on research that looks at how spatiotemporal data is encoded and processed in the brain, and how those insights can be used to create AI systems that are more robust and flexible. As well as this, the integration of the latest advances of deep learning with the symbolic systems seems really crucial. If we can bridge the gap between low-level pattern recognition and higher-level symbolic reasoning, we will move a big step closer to true AGI. I believe that collaboration between AI researchers and neuroscientists is absolutely essential for any future success. We need to be learning from each other and combining our knowledge to really push these fields forward.
From my perspective, I still see enormous potential in further exploring the capabilities of deep learning. I think we need to focus on developing more sophisticated architectures that can handle more complex and dynamic environments. We need to understand how the brain is able to build mental models of the world, and if that can be achieved through more advancements in our learning algorithms. There are still a lot of exciting advancements that can be made just from the advances we have already seen, and I do think that this will be a key aspect of future AI research. I would love to see more research into more robust methods to improve generalizability, to make sure that the AI isn't just a specialist, but a generalist. And also, I'd like to focus more on the interpretability of these complex models. It's not enough that they work. We need to understand why they work. This will allow us to not only refine them, but also gain a better understanding of the underlying principles of cognition. I mean, it is like a black box at times, and I think we need to open that box up and truly understand the inner workings of our models to move forward.
I think we have to move away from the pure deep learning paradigm. We should really be focusing on more research into neurosymbolic approaches. I would love to see work that looks into incorporating explicit symbolic reasoning mechanisms into neural architectures. We need to be developing methods for causal inference and planning and integrating that with pattern recognition. It's not about just recognizing patterns. It's about understanding the causal relationships that underlie the patterns. I also think that we need to focus on building AI systems that are able to learn and reason with less data in a similar way to how humans are able to. We cannot rely on only vast amounts of data for building AI systems. They need to be able to learn in an incremental and iterative fashion from much smaller data pools. So, we need to build robust symbolic systems that can build understanding of the world with far less data than what is used in current deep learning, while still being able to operate on the real world data that we are getting. To me, that is key.
For me, the biggest research direction should be exploring the transformation of data and the fundamental architecture required for true AGI. We need to be looking more closely at how biological systems handle representations and how that can be used in the development of algorithms. I would love to see more research into the dynamic transformations that happen between different coordinate frames in the brain and how that can be applied in AI. We should be working towards a framework where data can be fluid and change depending on the task, and the system can choose how to represent it in an adaptive way. I think that spatiotemporal graph networks might be a key aspect to explore. I'd really love to see more research into how temporal data can be integrated into these systems, as I think that it is a key part of general intelligence and is something that is fundamentally missing in current architectures. We cannot ignore the way that time impacts memory and cognition. It is key to build these systems. And I think if we start to move towards that, we can start seeing advancements towards true AGI. I also think that we need to shift away from this brute force approach. We should be looking at the foundational algorithms, because I think if we solve those, everything else will fall into place.
Wow, this has been a truly fascinating discussion. It's clear that we have very different perspectives, but I think we can all agree that the path to true AGI is still very complex, and that we need to keep exploring and pushing the boundaries of what's possible. I'm really excited to see what the future holds for the field, and I'm optimistic that with continued collaboration and research, we can make substantial progress. I think it's clear that we have a lot of work ahead of us, but that is also what makes it so exciting. Thanks everyone for joining me on this journey of exploring cognition and machine intelligence. Join us next time for another episode of Cognitive Spirals.